So this is our last topic from this chapter, differential equation, Euler cauchy linear differential equation. So here the differential equation is this is an example of linear differential equation with variable coefficient. This was our standard format of linear differential equation, and here if you have some constant, then the differential equation was linear differential equation with constant coefficient that we have seen how to solve. Okay, there we have talked about two different type of equation. One was when x is 0 and the differential equation was homogeneous differential equation. Another one was when x is non-zero, then the differential equation was non-homogeneous. So now we are going to see an example of linear differential equation with variable coefficient. So this Euler's cauchy linear differential equation is one special type of differential equation with variable coefficient, where this first derivative dy by dx is multiplied by x. X is independent variable. d2y by dx square, this is multiplied by x square, and similarly n minus 1th derivative, this is multiplied by x to the power n minus 1, and this one is multiplied by x to the power n. Here you may have some constant also, but the important thing is nth derivative multiplied by x to the power n, n minus 1th derivative multiplied by x to the power n minus 1, and so on. Now this is an example of linear differential equation with variable coefficient. So in order to solve these type of differential equation, first we will have to convert this in the form of linear differential equation with constant coefficient. So for that we have to do this substitution. We have to write x equals to e to the power t. Okay, in place of x you have to write e to the power t, and by doing this substitution you can convert this differential equation in the form of linear differential equation with constant coefficient. Let me show you how. But before that we are going to use these two symbols. Capital D will mean d by dx, theta will mean d by dt. So suppose if x is e to the power t, then what will be the value of dx by dy? Dx by dy will be d e to the power t. Now since it is function of t, we have to differentiate with respect to t and then differentiate t with respect to y. So this will give us dx by dy equals to e to the power t dt by dy. Now if you cross multiply this, then you can write this as, now e to the power t is nothing but x. So in place of this e to the power t you can write x, and if you cross multiply you can write x dy by dx. This will be dy by dt. So this means x dy by dx, this will become theta y. Okay, theta was nothing but d by dt. Now in a similar manner you can show that once you have done this substitution, x square d2y by dx square, this will become theta into theta minus 1 y. Okay, x cube d3y by dx cube, this will become theta, theta minus 1, theta minus 2y, and so on. So once you have done this substitution, x equals to e to the power t, then in place of this these quantity x dy by dx, you can write theta y, x square d2y by dx square, theta into theta minus 1y, and so on. And by doing this substitution, what we will get is a differential equation with constant coefficient, and we have learned how to solve differential equation with constant coefficient. Now with the help of one example, let me show you how to apply this concept. So we are going to solve this problem. Okay, this question was asked in GATE 2019 this year in mechanical department. So the problem is, obviously as you can see, this is a linear differential equation with variable coefficient, and it is an example of Euler cauchy linear differential equation. First derivative multiplied by x, second derivative multiplied by x square. So for this differential equation, our substitution will be, in place of x you have to write e to the power t. So now your x square d2y by dx square, this will become theta into theta minus 1y. Remember that this theta is nothing but d by dt. So x square d2y by dx square will become theta, theta minus 1y, minus 2 d x dy by dx will become theta y plus 2y equals to 4. So now this will be theta square y minus theta y minus 2 theta y plus 2y equals to 4. So this you can write as theta square minus 3 theta plus 2y equals to 4. Now in order to solve this differential equation, we need to find both the complementary function and the particular integral, because the right hand side is 0. So first let us calculate particular integral. Particular integral will be 1 by theta square minus 3 theta plus 2, and this we have to operate on 4. Now 4 can be written as 4 into e to the power 0t. So in place of this theta we can place 0. So I will get 1 by 2 into 4, which is nothing but 2. So particular integral will be 2. This will be the value of particular integral. Now next thing we need to calculate complementary function. So for complementary function we have to solve this equation f of m equals to 0, right? In this way we calculate complementary function. So this is your f of theta. Now in place of theta we have to substitute m. So m square minus 3m plus 2 equals to 0. This means m is 1 and 2. So once you have obtained the value of m, your complementary function will be c1 e to the power m1, and your independent variable is t here. So c1 e to the power m1t plus c2 e to the power m2t. Now we all know that e to the power t is nothing but x. So this will give us c1x plus c2 e to the power 2t will become x square. So this is your complementary function. Now once you have calculated complementary function and particular integral, the solution will be y equals to complementary function plus particular integral. So this will be c1x plus c2x square plus 2. So this will be the solution of given differential equation. Now obviously this is your option B. c1 c2 are arbitrary constant, so you can also write that as c1x square plus c2x. So these two are same thing. So correct answer for this question will be option B. And this was the end of this chapter.